So, do you see my screen? I hope so.
Yes, it works. It works very well.
Great. So, first of all, thank you, Mark, for the presentation. And also Mark, Lyubov, and Pedro, and everyone else in here. Thank you very much for the invitation. I'm very happy to be here in this network seminar at CRE. I'm very happy also to discuss with you during the talk and also a bit later about basically anything, including the startup work that we do and everything. But now I will try to focus a bit on the science. So I would like to talk to you today a bit about a recent work we did with some colleagues and friends in EANAS Leon, in CU, and also at Limerick University in Ireland, that has to do precisely with modeling dynamics of contagion on top of bursty temporal networks and seeing how burstiness actually affects the dynamics of these processes. Please ask any questions at any time, like it's completely okay. Mark, if I don't see a question or something, please let me know and interrupt me. It's totally okay. Great. So I'll just try to move forward. So I would like, just like the other time, I would like to start by reading you a quote that I really, really like. One by Richard Feynman, actually, in his very famous lectures on physics, where he's talking, about this idealized scenario of a cataclysm that destroys all knowledge on Earth. It perhaps sounds a bit similar to the pandemic times that we are having now. And he's asking himself what would be, this little piece of knowledge that by itself would be enough to replicate everything that we know about physics. So let me read it to you. I really, really like it. If in some cataclysm, all of scientific knowledge were to be destroyed and only one sentence passed on to the next generation of creatures, what statement would contain the most information in the fewest words? I believe it is the atomic hypothesis that all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. In that one sentence, you will see there is an enormous amount of information about the world, if just a little imagination and thinking are applied. I really, really like this quote, not only because it's beautifully written, but because it reminds me a lot something that my PhD supervisor told us in our undergrad physics classes in Mexico, in UNAM, while we were there. He was saying that actually, physics was something where memory was actually not necessary, because in order to know physics, you didn't need to memorize things. You actually only needed to derive things from basic principles, right? So there was just very little you needed to learn by heart, and everything else was just mathematics and rules of inference. So thinking about this, there's a question to be raised. So what would be kind of like the equivalent axiom in network science, right? What would be the atomic hypothesis or this very small piece of information that if we were smart enough, we could kind of like take over and replicate everything that we have learned about network science in the last 20 years? I guess there are many answers to this, but at least if you ask me, I would say that it would take a bit of kind of this shape. Structure determines dynamics, right? That if we are interested in all of these dynamical processes that happen on top of a network, then the underlying topological structure of this network is going to somehow determine what is the behavior of these dynamics. And if we understand this link between structure and dynamics, then we will really get kind of a deeper understanding of the system and the process as a whole. In one of the first, a classical example already up until now, but one of the nicest examples of this was the early work by Vespignani and colleagues on epidemic spreading in the early 2000s, right? When they took this archetypical epidemic model, the SIS model, and so what happened to this model when you actually analyzed it on top of a network. Already from the 50s in mathematical biology, it was very well known that when you analyze an SIS dynamics on top of either a completely connected network or a random network, then typically you have these two different stationary final states, right? So you have an area of the phase diagram in which you have epidemics, right? So a small seed of contagion actually spreads through the whole network. But if the different, then you also get another region in which you don't have an epidemic, right? And these two are divided by a so-called epidemic threshold, that is this critical value of infection parameters such that infection actually spreads in the world. Okay, but this only happens in the so-called completely or randomly mixed hypothesis, right? That everyone is kind of connected with everyone else. What is cool, and probably most of you already know this, if you have done a little bit of networks, is that if now you change the underlying topological structure of the network, and you substitute, says, a network Shreni network structure by a scale-free degree distribution, and one particularly in which the scale-free exponent is between 2 and 3, then what will happen is that this epidemic threshold will disappear. No? You can, under the heterogeneous mean field approximation, you can derive or at least approximate this epidemic threshold as a ratio between the first two moments of the degree distribution. And since in a scale-free network where the exponent is between 2 and 3, the second moment diverges, meaning that the degrees are very heterogeneous and the tail is very long, then this threshold is going to disappear, right? So then all of a sudden what happens is that you don't have a region in the phase diagram in which there are no epidemics. Epidemics will always happen irrelevant of the parameters of the model, right? So structure indeed determines dynamics, right? We need to pay close attention to what happens in the underlying structure, because whatever process happens on top is going to depend strongly on this. After this type of results, people got very enthusiastic, right? They say, oh, okay, so wow, we have like, you know, some analytical techniques, and we have a relatively general framework that can, you know, specify dynamical processes on top of networks. What about if we apply it to all of the dynamical processes that we would be interested in, not only biological processes, but in particular social and cultural processes, right? We can think of processes like epidemic spreading and social contagion, or even other things where the states of the nodes are actually opinions, right? Or where we are interested in the way information is spread from one group of people to another, or even cultural dynamics, and or something that now is very important because of its consequences to epidemic spreading, the idea of human mobility, right? Like humans are actually moving from one place to the other, and we can actually understand this process with the same type of mathematical constructs. So all of this sounds really, really nice. So then, you know, like, and people were analyzing these kind of in particular cases, right? So they had like a specific mathematical structure to analyze opinion formation, and then another one for social contagion, and so on and so on. But one kind of question that started appearing here was, okay, if indeed there seemed to be such a general link between, you know, what the underlying topological structure is and the dynamics on top, maybe you can really write analytical frameworks that analyze these processes in a very general way. And here is where, you know, like one of my favorite scholars in the world, James Gleason, comes in a few years ago, right? And he actually proposed one such framework, which he called approximate master equations for binary dynamics. So what he did is something like this. It's like, okay, let's assume that we have a static network, right? So a configuration model network with a given degree distribution and no, for example, degree correlations between the nodes. Fine. And then we have some specified binary dynamics on top of it. Binary meaning that we only have two states, like susceptible and infected. And then the nodes, according to certain rules of the model, are transitioning between the state of susceptible and the state of infected, right? And then his idea or goal was to try to determine a set of master equations, meaning rate equations, that would specify what are the transitions between these two states at a certain level of approximation, and therefore determine the whole dynamics of the system. And what he found, or kind of, you know, the trick or the essential idea of this framework was to actually separate all of the nodes into classes, depending on two particular variables. One is the degree k, no, the number of neighbors you have in the static network underneath, and the second is the number of infected neighbors m, meaning say if you are in the susceptible state 0, then it's the number of neighbors you have in the opposite state. Right? Once you do that, then you can define a so-called equivalence class of nodes, SKM, which tells you the fraction of nodes that have degree k and number of infected neighbors m that are susceptible. And equally, you can also define the fraction IKM, which is the fraction of infected neighbors that have degree k and number of infected neighbors m. With these two, now you establish this, you can actually write rate equations, master equations for the basically the transition rates of these quantities, right? How these two dynamical fractions of nodes in this equivalence class are actually going to evolve in time. You think a little bit about it, and it turns out that these master equations actually is a very large system of coupled differential equations. How this one is actually determined by two transition rates that are called the infection rate, FKM, that regulates how nodes are going from susceptible to infected, and also the recovery rate, RKM, which regulates the opposite rate, right? Going from infected to susceptible. So forget about all of the details here. What is important? What is important about this is that the master equations, like the shape of the master equations, regardless of the model that you are analyzing, is going to be the same. And the only thing that will change from model to model is the actual functional form of these two rates, F and R. So actually now what we have done is taken all of these two of possible models, epidemic spreading, opinion dynamics, cultural formation, human mobility, and all of these things, and try to write them into the same analytical framework, but where the only two variables, in a way, are actually these two sets of functional forms, the infection rates and the recovery rates. So now what we need to do is analyze this functional form from one model to the other and see what the overall effect is going to have in the dynamical behavior of this system of equations, right? So for example, you can start seeing certain things. If you analyze very simple epidemic model like the SIS model, it will turn out that the infection rate is linear in K, which makes sense, right? Is linear in M, okay, which makes sense, right? The bigger the number of infected neighbors you are, linearly, the larger the probability that you're actually going to change state, right? And so on and so on. So and here, like the idea is that you can take any dynamics that you want, you figure out what is the functional shape of these transition rates, and then you can solve the equations. Here, there's a table that appeared in one of the first papers by Gleason, where he does precisely that, right? Just to show you, like a small subset of dynamics that up until that time were very famous, the SIS model, the SI, the vast diffusion model that is used in management, the voter model, archetypical model of opinion dynamics, the language model, Ising models used in physics, and each one of them you can actually write explicitly the transition and the recovery rates, and therefore you can solve, or at least you can attempt to solve, the AMEs in any way you want. There's a slightly more technical detail that I also really like about the AMEs, is that in a very natural way, they actually kind of lead you to a hierarchy of approximations. Because as it turns out, the AMEs, as you can probably see from here, it's actually a system of equations, right? So in here, I have two equations for each group or for each pair of values of K and M. But if your network is heterogeneous, meaning you have a lot of values of K, you will have many equations, right? So so in principle, this is a very large system of hundreds or thousands of equations that are coupled and non-linear, right? So this is very difficult to solve. I mean, you can try numerically, and in some particular cases, you can even do analytical stuff, right? But the idea is that, yes, it's a very large system, but it's very precise, right? So when you compare it with, for example, Monte Carlo numerical simulations, then you get something relatively close to the real answer, to the ground truth, the numerical simulation itself. But what it turns out is that then you can take these approximate master equations, make certain approximations in the equations themselves to reduce the number of equations, lose a bit of accuracy, but get a system that is smaller. Okay, so it turns out that you can do this and move from approximate master equations to so-called pair approximations, in which the only information that you are capturing from the system is actually the joint distribution of node states. And then you can make even more approximations to reduce further the number of equations and end up with something very similar to the typical mean field approximations, like the heterogeneous mean field approximation that Vespignani and friends were using to analyze the SIS model and see the effect of a scale-free distribution. This type of mean field approximations that basically consider that all potential correlations, dynamical and structural, basically don't make any effect at all, right? So we have this very nice kind of hierarchy and approximations. And it turns out that depending on the dynamics that you're talking about, depending if you're talking about epidemic spreading or opinion formation or social contagion, some of these approximations will be similar to each other in terms of the final stationary states that they define, and also the dynamical behavior and transient states. But in some particular cases, this is not the case, right? So for example, the mean field is going to give you the wrong it's taking you to a different stationary state than the real one, and then you need like better and better approximation. So again, it's kind of a very flexible framework that lets you kind of have some intuition of the approximations that are being involved in the type of analytical calculations that you're doing about your system. So a few years ago, with some friends, we got very excited about this, right? It's like AMEs, wow, you can do anything that you want with them, right? So we decided to little by little kind of generalize or extend the original AMEs that were initially only made for simple networks. So the configuration model framework with only simple links, and that's it. And little by little, we try to generalize these to see what happened to the AMEs, right? So we went from simple networks to weighted networks. You have a weight on the links, to multiplex networks. You have now several layers of network connections between the nodes. And finally, even now we are working with higher order networks in which you are considering explicitly some sort of simplicial connections between the nodes, between groups of nodes, right? Overall, what we have seen is that the AMEs are indeed quite flexible, because the only thing you need to do is remember there was this so-called equivalence class of nodes, right? So I'm taking all of the nodes that have degree k, a number of infected neighbors m, and I'm considering all of those nodes to be statistically equivalent, okay? They are described by the same rate equation, and therefore they have the same statistical behavior. So the way to generalize these AMEs to more and more complicated network structure is basically to select the correct equivalence class, okay? To generalize this pair Km to something else that characterizes the group of nodes that are statistically equivalent, and then just rewrite all of the equations. And in general, what happens is that, K will be transformed into a vector K, a vector of degrees that specifies the node. For example, the degrees at different layers of a multiplex network. And the number, the scalar m, is also going to be transformed into a vector m of the number of infected neighbors that you have in different layers, and so on and so on. Again, maybe you are guessing already from now that if the system of equations was already big, these generalizations are going to make it even bigger and bigger, right? So you are actually like increasing, sometimes even exponentially, the number of equations that you are going to solve. But again, in some circumstances, you can do some analytical tricks, for example, for the Watts threshold model of social contagion, and reduce this system again in certain situations, right? So there's a lot of like really interesting things that you can do there. So, like you say, okay, all of this sounds great, but let's try to go to the topic of this talk and what I want to talk to you in particular. Let's think about yet another quite complicated but relevant feature of real networks, and in particular social networks, which is the fact that these networks are actually not static. Okay, like a big assumption that has been made in the AMEs from the beginning on is that the degree is constant, right? So the underlying network is static, and therefore this quantity, this k, is constant in time, right? If you belong to a class with a given value of k, you will always have that value of k. So this drastically simplifies the system. But we started to question ourselves, well, what happens if that's not the case? Because we know that in reality, most social networks are indeed temporal. A lot of people have been working on this, and they have like basically two general ideas of conceptualizing temporal or networks that change in time, right? On one hand, we have what people call dynamic networks, right? Which points a bit to the fact that the shape itself of networks is changing in time. You can think of a social network, and the nodes don't have to be there all the time, right? So nodes enter the system, so nodes go away, these networks start growing and decreasing in time. So there's some type of dynamics specified by certain timescales that is telling us how these networks are changing in time. On the other hand, people have also realized that in some specific empirical scenarios, networks are in a way better defined as a sequence of snapshots. This is particularly important in the case of mobile call sequences. For example, you have people, these people are, like in a particular moment of time, not connected between them, but then one person makes a call to the other person, right? So during the duration of that call, these two people are actually connected, but once the call ends, that link disappears. So when you put all of this data together, what you have is a temporal network, meaning a sequence of snapshots, and each snapshot is a static network that only lasts for a very small period of time. right? So now what we need in a way is to take all of the tools that we have been working on in static networks and somehow generalize so that they can apply to this specific case of temporal networks. One of the earliest results of temporal networks, and in particular of systems that can be specified as sequences of events, was this idea of burstiness, right? That if now you would, for example, focus on a particular link, no, the potential link between nodes IJ, and you see the sequence of events that happen in that link, it turns out that the sequence of events is not random, it's not homogeneous, but it's actually something that is called bursting. Okay, so most of these events are actually kind of, like structured as certain periods where a lot of events happened, and then very long periods where nothing happens. If you quantify this as the so-called interevent time distribution, which is the distribution of the time happening between two consecutive times, then this interevent time distribution is going to be scale-free. Okay, it will have a long tail, meaning again that most of the interevent times are very small, so they correspond to the bursts, and then every once in a while there's a very long time that corresponds to the time between bursts. Okay, so then this is really cool. Like people were working in static approximations of dynamical processes over networks, and then some other people started working on temporal networks, and then people started getting very excited, right? Because they said, okay, let's try to put these two things together. Let's see what happens, or what is the effect of having an interevent time distribution, and particularly a bursty temporal network. What will the effect of this temporal network structure going to be on the process that is on top of it? And then, boom, there were a million studies. And as it often happens in science, which makes it interesting, but also a bit confusing, results started going kind of in opposite directions, right? Some people, for example, focused on epidemic spreading models, particularly an SI model, and then they started to try to explore what was the effect of burstiness on epidemic spreading. And some papers started saying that, like burstiness actually slows down epidemic spreading. But then there are a few other papers that said that in other toy models and in other data sets, it actually sped it up, so it made it faster. In the same way, some people started focusing on social contagion, on the so-called threshold models, in which you are interested in the process by which, for example, a node gets infected if a certain fraction of the nodes around is also infected, okay? Therefore giving rise to a cascade of contagion. And again, according to some people, the presence of burstiness would make this process faster, and according to some other people, it would make it slower. So then, which is it, right? And this is where we come in. We were very much interested in trying to clarify this link as much as possible, okay? To really try to put these two things together, meaning a dynamical process written in terms of AMEs, and also a bursty temporal network written in terms of an interevent time distribution, put these two things within the same analytical framework, and finally kind of, find a systematic link that tells us that this amount of burstiness is going to either slow down or speed up this particular dynamics, right? To try to give a bit of a clarity, perhaps, or a little bit of analytical insight to all of these empirical results that were a bit before us. So let's try to do that a bit more in detail. Great. So how do we start, right? So the first thing to start is to set up a temporal network in a way that is friendly to the AMEs, right? So what do we do? First, there are many ways of doing this. But this is the one that we decided to take into account. First, you start by kind of defining an underlying potential network, right? So you can think of it as a network of invisible links over which the actual links corresponding to the temporal network will appear and disappear, okay? So this invisible network below, we will, assume that it has a degree distribution pk that can have any shape. For example, we will approximate it by a log normal or scale-free distribution, right? There it is in there. Then, on top of each one of these potential links, then we will define a point process, independent point process, that follows an interevent time distribution psi of tau, okay? So what is going on? That in each one of these links, for example, the link between the node U and the node V3, then you can think of a time series determined by an analytical point process, Okay, that is defining at what times events are appearing. This can be instantaneous phone calls between these two nodes, for example, right? But the inter-event time distribution between these two, between any pair of times in here is determined by this distribution that we set up as a parameter of the model. And that's it. Then what we do, we need to discretize this process in some way, right? So something that we do is that we define what we call a memory window of size eta, such that at a given point in time t, we only see or we only consider the events that have happened on a memory window of size eta to the past. Okay, and then we keep sliding this window as time goes by. So what is the overall effect of this? And I hope you agree with this with me, that we have basically created also equivalence classes very similar to the ones of the original AME framework, but now for a temporal network. Why? Because now we can define a new time varying degree, which we call kj, which is the number of neighbors you have with nodes with which you have had j events in a window, in a memory window of size eta. Okay, so you're moving in time and you have all of your potential neighbors, and then events are happening. And then all of your neighbors are kind of constantly changing from having a certain number of events with you to some other number of events. And therefore your degree is changing all the time. But it changes in a discrete way because we have defined this memory window. Okay, so it goes from 0 to 1 to 3, back to 1, and so on and so on. So you will have now transition rates also in your degree in the same way as with the dynamical process, as we will see in a second, you will also have transition rates in the number of infected neighbors. So we are just, yet again, just like a long time ago in here I said, we're just taking this pair km and we are generalizing it to some sort of vector km class that is a bit more general, but takes into account the dynamics of the temporal network. Cool. So that's the part of the network, right? And then, just as before, you have to determine the dynamics, right? The model that you're interested in. AMEs are general, so you could take any model that you want, but for the sake of presenting results for something, we focused on 3 models, right? So we took the susceptible infected model, SI model, everyone knows it, right? So you have a constant probability lambda of going from susceptible to infected, but this is a monotonic dynamic, so you don't go back. So there's 0 probability that you go back from infected to susceptible. And then we also take a couple of archetypical social contagion models, the so-called threshold models, in which you only change state from susceptible to infected if either a fraction or a certain number of your neighbors is already infected. Okay? You think a little bit about it, and then you can write this transition rate, meaning the rate or the probability per unit time of going from susceptible to infected. You can write these 3 probabilities in this way. Just to make things simpler and try to compare the 3 models, we also add a very small amount of noise parameterized by a parameter p, right? So then we have this process that is driven either by epidemic dynamics or by social contagion, plus a little bit of random noise. And this is the dynamics. Okay, so what you see here is basically the model, right? So now we have put into place all of the pieces that we need in order to determine the AMEs, right? The dynamics of the temporal network specified by the inter-event time distribution psi is telling you what are the degrees of the nodes and how these degrees change in time. And then each one of the models, as encoded by the transition rates FKM, are also telling you how the nodes are changing state from susceptible to infected, right? So now what is left after this is to actually write the AMEs to generalize these approximate master equations like we had them in the very original case by Gleason. So that's what we do, right? And I'll try not to go too much into details into the actual equations because they're huge, but I will just try to say a bit of the intuition of how they work behind, right? So it will, and I will put it, as putting how these AMEs work in the static case, and then how they work in the temporal case, and basically what is extended, right? So it turns out that typically, or like these AMEs or these rate equations have 3 terms. Okay, the first term depends on the ego, on the node, right? On the node in the class KM, that is the one that you're interested in. So that first term that I put in here, that is basically proportional to F and S, is telling you what is the rate at which you will change state from susceptible to infected, right? So this only depends on the transition rate that we have defined already before, the ones that we put here, and depends on each one of the models, right? Then the second component of these rate equations will depend on your neighbors, right? Will depend on the probability with which each one of your neighbors is also changing state. If we would have a static network, then that's it. We only have these two terms, right? You only care about what happens to the ego and to your neighbors, and that completely characterizes the dynamics. But what happens is that when you move to temporal network, you have a third element in the equations, right? Because now the network itself is changing, your degree is changing. So even if none of the nodes in your neighborhood change state, you can also leave the equivalence class Km. Your degree changes, right? So your K is not K anymore, now it's K plus 1. So then you also left that group. Okay, so there will be certain probabilities of changing state, of changing equivalence class by keeping the same state that you have, but by gaining or losing edges. So you think a lot about this and you do all of the math, and you will come up with a table like this one that we have in our paper, right? So you can explicitly write each one of these terms, the term corresponding to the ego transition that is in orange, the neighbor transitions in blue, and all of the edge transitions that are separated in two cases, right? The transitions in which you earn one extra link, which are in green, and the transitions in which you lose one link, which are in red. You think a little bit about it, and it turns out that you can actually write these two rates corresponding to the fact that you earn or you lose one link, mu and eta. And these two transitions can be written explicitly in terms of some relatively complicated convolutions of the original interevent time distribution psi and also its cumulative distribution function. If your interevent time distribution is sufficiently well behaved, as in some of the cases that we're going to analyze, then you can even solve some of these convolutions exactly. But of course, if you're doing data-driven simulations and you are taking your interevent time distribution from data, then you just have to solve these things numerical or with Monte Carlo simulations or something like that. Cool. So yet again, basically the framework is done, right? So first we specify the temporal network. We have the models that we are going to use. Then we finally write the master equations, a huge system with a lot of different terms, but we know what each one of the terms is doing. Now we just have to simulate this system and see what is the effect that in particular the interevent distribution is having, because that's the thing that we were interested in, right? So the first thing we do is that we need to set up some typical cases for all of the parameters and functions that are here, because the system is a bit of a zoo, right? There are like a lot of moving parts. So what are we going to take? For example, for the interevent time distribution psi, we take a Weibull distribution with a tunable standard deviation sigma tau, and also a certain mean interevent time distribution. Or you could also just take empirical data from some distribution, right? Remember the underlying degree distribution over which the temporal network is appearing. So for that one, we take a log normal degree distribution, also with a tunable standard deviation and mean. And finally, from the three models for what I will show in this slide, we in particular take the relative threshold model that has a certain threshold phi and a very small noise parameter p. Okay. That's kind of like the setting for the model, and then in physics ways we need an order parameter, right? So we need something that tells us what is happening in the system. And since I told you a bit before, what we are particularly interested in is the speed of contagion, the speed of the process, then we need some measure, right? Some measure of how fast the process happens as a function of all of these moving pieces. There are many ways of doing this, but the one that we eventually settle on is something that we call the density of noise-induced infections, right? Because as you saw in here, and I tried to say in the beginning, so we have kind of, a rule described by this transition rate that's telling you how you go from susceptible to infected, but you also have a noise rate, P, right? So basically, there are kind of like two dynamics driven, one driven by the model and one driven by noise. And you can separate these two, no? And an idea of the speed of the process is kind of the difference in speeds between these two processes, between the one actually driven by the model and the one driven by noise. So you can do this by calculating this. Is basically the relative fraction of nodes that have been infected due to noise instead of due to the model. Okay, we call that this rho of f. And then it will turn out that if rho of f is small, meaning there are not too many infections induced by noise, then your cascade is fast, right? Because the model process is happening so quickly that you don't have time for noise to do something. Remember that the noise parameter, we always choose it to be very small. But now imagine that this noise rate is very large. Then that means that the cascade, the dynamical process has been so slow that there is time for noise to actually do something. Therefore, the cascade is slow, right? So then this rho f is going to tell us a bit kind of like the relative speed of the process. And we are interested in seeing what is the area in parameter space, in particularly with the interevent time distribution, that leads to either big values or small values of rho of f, okay? This density of noise-induced infection. So without talking more, let's see the results, right? So what do we have in here? Here you have in the x-axis the standard deviation of the interevent time distribution, okay? This sigma of tau. And then in the y-axis, you have the logarithm of this density of noise-induced infections. Remember, if it's big value, it's a fast cascade. If it, sorry, the other way around. If it's a small value, it's a fast cascade. If it's a big value, it's a slow cascade. And in terms of the x-axis, if the standard deviation is small, then we don't have burstiness, right? Because that's a very homogeneous interevent time distribution. And on the other hand, if your standard deviation is very, very large, then you have a bursty system in which the interevent time distribution is very heterogeneous. All right. What happens? What happens is that when your system is basically regular, okay, when the events happen on top of each one of the nodes in a regular way, you have, and remember, and this is the threshold model, then your system is relatively slow. Okay, that's the left. But then you add up a bit of heterogeneity and the system speeds up, okay, becomes faster. But then if this is kind of an optimal moment around the Poissonian limit, because then if you make the system more and more bursty, actually you slow down the cascade. The system is way too, as we will see a little bit later, actually is too sparsified in between the bursty trains, and then your dynamical process is actually slower. It is interesting that you can choose some other order parameters, right? So in here we selected this density of noise-induced infections, but actually you can choose something else. For example, the typical time at which a cascade happens, at which a very large fraction of the network is actually infected. And these two quantities, you know, this noise of induced infections and this critical time to a cascade correlate very much between them. Okay, so this overall effect that we see of slowing down or speeding up due to burstiness is not really dependent on the quantity that we use in order to determine the speed of the process, right? So you can take 0. We saw this as a function of the standard deviation. You can do it as a function of some other parameters. And in particular, here, what we have is the same effect, but opposite, when you make it as a function of the memory window. Remember that eta was the size of the memory window, right? So again, this is a way of kind of like regulating a bit the sparsification of the system, right? If your memory window is very, very small, you are never considering events, right? So your network is really, really sparse. But if you make the memory window bigger and bigger, you are considering more of the memory of the system, whatever has happened before, and therefore you have really, you know, like you have your temporal network becomes more and more dense. What happens is if you see these two figures is that you get kind of a mirror effect. Okay, so again, we have this process of if the system is basically memoryless, it's slow, then it gets faster, and then it gets slow again because the system is way too dense. Cool. So what we did, this was for a particular model, and the relative threshold model. then we try to do the same, but also for the other systems, right? Remember that we had the absolute threshold model and also the susceptible infected node. So the susceptible infected model. So here are the results. So again, the underlying potential degree distribution is this log normal with a certain mean set. Then on the upper row, we have the absolute threshold model. So very similar to the relative threshold model, but now you consider the number of nodes that are in the opposite state in order to adopt. And the lower row is for the SI model, the typical susceptible infected model. Okay. The x-axis in all of the cases is the standard deviation of the interevent time distribution, just like before, separating between regular, Poissonian, and bursty cases. And then the y-axis is this rate of infections by noise, just like before. So what are you seeing here? Remember that before we had kind of like this case in which we go from slow to fast to slow. In the other case, in the other threshold model, something similar happens as well, right? You go from kind of slow to in the middle to fast, and in here as well. But there starts to be some effect of the threshold itself, which didn't happen before. Okay, so there are some cases, depending on a parameter of the model, in which actually you always go from like really fast to slower and slower, and particularly in the susceptible infected model, you only have two cases, okay? Poissonian and regular interevent time distributions will always lead to fast cascades, and when you add up burstiness, you always slow down the dynamics. I always like to think of this in a statistical way, because remember that these are the papers that I showed you here, when there were, like many papers that were saying that susceptible the SI model, burstiness in the SI model led to slowing down, and only one or a couple found the opposite effect. Well, this kind of, like is very compatible with what we see here, So kind of cool result in there. So what is also kind of nice, again, in the physics tradition, is that we can make these curves also collapse by doing a proper rescaling of the parameters. So I've been hinting a couple of times up until now that a lot of this, or the effect that burstiness is introducing into the system, is kind of a sparsification of the temporal network, right? So you kind of, like if you move the memory or if you move the standard deviation, then you kind of regulate a lot the number of links that appear in the system in a certain point of time, and therefore you are like effectively sparsifying the network. And something that supports this hypothesis is that then we can scale these quantities in that way by introducing something that we call effective sparsification, right? Which is, in few words, the density of edges in this state j equals 0, meaning the density of edges that don't have events on them. Okay, remember that the state j0 is the one that I showed you here with the memory window, right? So if no events have happened in your memory window of size eta, then your state is j0. If one event happened, then it's 1, 2, 3, and so on. Okay. So if your density of edges in state j0 is very large, then it means that the network is sparse. Right. So if now we take all of these curves, but we don't plot them as a function of the standard deviation of the interevent time distribution, but as a function of this so-called effective sparsification, then all of the curves collapse onto each other, which is kind of awesome, right? And in there, this effect is even clearer. Would you take the threshold models, and indeed you have this type of curve that goes from slow to fast and then to slow again. But if you go below to the SI model, then you have a universal curve that only goes from slow to fast. So this is kind of like, this is our result, right? So we have a way of taking AMEs that can take any type of model, dynamical binary model on top of a network that you're interested in. You mix it up with a temporal network regulated by a specific interevent time distribution, and the AMEs are going to eventually lead you to a universal curve that will tell you, relative to the effective sparsity of the network, of the temporal network that you have, what is the overall effect on the speed of the dynamics, right? So answering our previous question, and just to try to end the talking here, what we were saying is that we take the dynamics, any dynamics, epidemic spreading, opinion formation, social contagion that you're interested in, you add a burstiness, and then the result of this, analyzed through this very systematic analytical framework, is that most of the times, depending on your model, burstiness is going to lead to a slowdown, particularly in epidemic processes. But sometimes for specific values of the parameters, and particularly for threshold models, you can also speed up this process due to certain amounts of, not too great, but certain amounts of burstiness. So well, the thing is that this is really cool because, like kind of like clarifies a lot of the things that some of the previous results that were a bit all over the place, precisely because people were working with empirical data sets. There are a lot of sources of noise, toy models that sometimes it's very difficult to compare to each other. So once you put all of this into kind of a very flexible and unified analytical framework, sometimes it helps you see things a bit more clearly. Great. So basically, that's it for me. I just leave for you here the link for the paper and a bit of marketing at CU. We have a few PhD positions every year, and also now we have a professorship open, and that probably some of you have heard. And there are also some of our contact details in case you are interested in talking with us. Thank you very much again, and please ask all of the questions that you wish. I'm very happy to help you and answer. Thanks a lot.
Thank you. Thanks a lot. Very, very impressive talk. Maybe, I want to play the devil's advocate. Can I begin by playing the devil's advocate?
Sure.
I have a question but that's obviously, like your models are beautiful. Now, what I wonder is that in real life, when you activate in a temporal network, you activate links, what happens is that and I expect that's probably a direction you're taking, you're activating very correlated links. Like I'm going to the family, I'm always activating a set, for example, of edges that are next to each other, right? So there's correlation between the links you activate because there are clicks. There's like, it's kind of a stochastic block model kind of thing. So yeah, so I was wondering in that context, whether that would change some of the results, in particular because I was wondering with your results that the absolute threshold versus so I was wondering about the intuition on that and how that plays with like this kind of small degree nodes, or like maybe if you give intuition and say what you would think with compartmentalized kind of models, how that would change things.
Definitely. Yeah. Thanks, Mark. That's a very good and relevant question, and it's completely true. I think the main simplifying assumption that we do so that we can actually do something with this model is this independence condition that you very well pointed out. So we are basically kind of, in a way, we're not considering a temporal network, right? We are considering separate edges.
Yeah.
And each edge is just, it has a, like a point process on top of it. That in itself is taking into account some memory. So there is a correlation with what has happened before. And even though it's a correlation that is very easily tractable, right? We even show in the paper that it can be mapped to a Markovian process anyway. So it's not really memory. But then the thing is that this is completely independent from what happens in other links. That's why later on you can write these transition rates so that you win and lose links in terms of these convolutions. If there will be correlations, then you cannot do this. So in principle, my first guess is that these terms in here would change completely because of the correlations, right? And that would have a very interesting effect. I have no idea what would happen, but exactly if we would take those correlations into account, quite probably these universal curves that we see here would change shape, which makes me think of all of these empirical results in here, right? Because, for example, in some of the cases in which, like they found that epidemic spreading was being sped up by burstiness, even if everyone else was finding a slowing down effect, maybe it was because of the correlations, right? Like their system was like heavily correlated in a particular way that is leading to this. right? So we are actually not invalidating that at all. We are just saying that, okay, if correlations don't happen, this is what you get, only a slowing down process, but still something different can happen with correlations. So that's super interesting.
Okay. Yeah, so very good. So, and maybe still, because I still can talk one question. I'm trying to build my intuition on why you find this early uptake, this early slowdown in the absolute threshold model, but not in the other one. And I'm still not able to fully make my mind of why that would be the case, and whether it holds with all types of degree distribution you've tried, or what's so because it's linked to the low degree.
Yes.
No, do you have an intuition on the reason?
Yeah, this is interesting. What I feel is that in this case, and of the absolute threshold model with very low m, that means that your threshold number is small, right? You only need one infected neighbor in order to adopt. So what I think is that in here, kind of like the dynamics is behaving kind of like an epidemic spreading dynamics. It's behaving like an SI model. That is a bit my guess. While in the other one, so with a relative threshold, so then it's always a fraction of the node. So then there's an effect of the degree. But in this case, the degree doesn't matter. So then what matters is the number of affected neighbors. So then I feel that it's more like epidemic spreading. It's more SI-like. But that only happens when your degree is small enough. If it starts getting larger and therefore starts getting closer to the actual degree of the node, then something different will happen. This is my guess, but I'm not entirely sure about what happened. That's an interesting case as well.
So are there other questions in the audience from the modelers here?
I would have a question.
Sure.
So basically, it's most of an understanding question. There are like several parts of it, in fact. The first is that I didn't really understand how you modeled the temporal evolution. So why, for me, it's important. I would like to understand this because, for example, have a Poisson process, okay? And suppose that there is one event happening at some point. Then the transition from this point to plus delta t has some probability that there will be in delta t another event. Now, if I move plus epsilon, then due to the memoryless property, the probability will be the same.
Mm-hmm.
And so I don't understand how, for example, you model this in your memory window eta, how we can see, because I mean, from what I understand, this dynamics that you have with partial equations, differential equations, they are based on the mean value, not the variance. So you have a mean value that is defining these. You have the rate of events, right? And so I don't understand how you move from the mean value of events to include also other moments of these events in the equations.
Okay. Okay. Let me see if I understand. There are at least two questions in there. I think there are more. But let me see.
Same, basically. Yeah, it has to do with modeling, right?
Yeah, exactly. So let me see if I can answer at least the first one. So, okay. So this is about how we simulate. So we have a dynamical process and it has two parts, right? So we have to simulate the transitions of the nodes from one state to the other. And we also have to simulate the network. Yeah, so how does the simulation of the network work? So we have the nodes, and we have this underlying network structure that is static, okay, with a certain degree distribution, a log normal. Okay, so we have links that exist and links that don't exist. So then each one of the links that potentially exist, we will consider it independently. Then run a point process on top of it in time. Okay, so for example, we take the node, the link ij, independently of the rest of the network, like nothing matters, and then you just start, like generating links, events on top of that link, according to a point process that is determined by a given interevent time distribution, a Webull or a log normal. So these are the lines that are in here.
So,
right?
but before we move on, this distribution, is it does it have this? Is it a renewal process?
Yes, this is a renewal process.
So this means that every interval is independent of the others. Okay,
Yes.
already. Okay.
Yeah.
Okay. So if it's exponential, it's a Poisson. If it is something else, it's something else.
Exactly.
Okay.
Exactly. So you can take a Poissonian renewal process. So the distribution is exponential, or you can take something with a long tail. For example, the Webull distribution that we are using, it can be a log normal, or it can be whatever you want.
Well, you could use something simpler also. For example, some I don't know, hyper exponential or right, combination of
Actually, in principle, the framework is completely flexible in that respect, right? Because it's just an input to the. So you choose whatever functional form of this interevent time distribution you're interested in, and you can solve things.
And now we start what I didn't understand. Okay.
Exactly. So now you have that point process. Perfect. So now the crucial thing is that, as you correctly said, this is a continuous process, right? So but since the AMEs are in a way discrete, meaning that I need a discrete number of equations, then
they are not because they are continuous in time.
They are continuous in time, but they are discrete in the number of equivalence classes that you have of these KM classes.
VMs and the Ks, yes.
Exactly. In that sense, it's discrete. So we needed a way, an artificial way, to be honest, to transform this continuous in time renewal process into something discrete such that we can define an equivalence class.
Okay.
So again, this was, by the way, a big discussion we had with the referees. I think there are many ways to do this, but one of the simplest ones is by defining what we call a memory kernel in here, right? So like a way of transforming this continuous point process into kind of a discrete degree.
But this is what my problem is, that your analysis lives in two worlds. It has the continuous time of each ODE and the discrete time of the window. And so this was my question: how do this get together? How do you move as the time moves in the one ODE? How do you jump to the next ODE?
So what happens is that, how to say, maybe in the simulation is clear to see. It's like, imagine like a numerical simulation of this, right? So I have a time counter. So I'm just, and independently, I'm just, generating the events and storing in memory at the times at which this has always happened, right? The times at which the events have happened. Then at any point in time, I have a memory of size eta. So I look to the back and I count how many events have happened in the last eta time steps with some unit, right? And that is always a discrete number. And that discrete number is going to be the state of your degree.
Yeah,
right?
I see.
So it will be that we call the edge state. So the state of that link. You can think of it as a time-dependent weight of that degree. It's kind of a weighted network. So by doing this, and that's the way we deal with these things. So we have a continuous temporal network, and we are transforming it into a temporal weighted network.
And the size eta, how do you select?
Oh, yeah. That's why I think, and let me see where I find it. We found this so cool because in principle, you don't have any, like a priori reason to choose one eta over the other. But what you see here in the lower part is that precisely the value of eta, the memory, also affects or like determines what is
the results, I guess. Yes. You know why? Because especially non-Poisson cases, this will have a lot of information, whether it's longer or shorter.
Exactly. And what is, I think, and we found it very cool, is that the effect of this eta, precisely the effect of this memory window, is the same but mirror to the effect that we saw with the standard deviation of the interevent time distribution. if you see these two curves are kind of like this, are the other way around.
Okay, okay, thank you. I will need to read it a bit more carefully also, but
Definitely.
thank you very much for your.
Yeah, no, this is very insightful because really, like we were thinking a lot about that particular detail. No, like we have you need to move from something continuous to something discrete.
No, I understand that it is necessary because you will not have any closed forms or specific expressions.
Yeah.
If you don't do that, but still, I need to understand a bit the trick. Okay, thanks.
Sure, thanks a lot, and we can of course discuss about this later on.
Of course, thank you.
We're a bit over time now. Are there any other things? Otherwise, if not, I think we can definitely thank you for presenting the very dense paper that we all need to read now.
It's very dense.
Okay.
Yeah, tell me about it. It's really, really dense.
But I can see that there's a line of prior work as well that we need to digest, but it's very good. So thanks a lot for your presentation. It was very interesting. And maybe, Liba, do you want to announce the next network seminar that there's going to be? Is it already planned?
Yeah, there will be one which will be on the 24th of June, which will be on the auto scene. It will be together with City Interaction Lab, and it will be more about the analysis of car data, but also from kind of urban and design perspective. So it will be really also like dense talk, not mathematical, but more actually from kind of perspective of philosophy of data. So come and yeah, hope to see you on the roof or wherever in space and time.
All right. So
yes, thank you so much for coming.